Hi everybody, welcome back. Today's lesson and lab are on electromagnetic induction. Let's cover the objectives of this lab. They are to discover the different attributes that affect magnetic induction. Alright, let's cover electromotive force. Electromotive force is a potential difference between 2 points that is measured in volts. Electromotive force is simplified to EMF, or the Greek letter epsilon. Note, electromotive force is not a force. Let's go over induced electromotive force. Induced electromotive force was founded by Michael Faraday's disgenerator experiment. Induced EMF is the creation of an electric potential due to a change in magnetic flux over time. Well, what is magnetic flux? Flux is denoted by the Greek letter phi. Flux is the quantity of magnetic field lines that pass in a perpendicular direction through a given surface area. The equation for magnetic flux is the magnitude of magnetic field lines that are perpendicular to the surface times the surface area. Magnetic flux is measured in Webers. Tip: when finding the magnitude of magnetic flux, multiply the value of phi, given by the equation above, by the cosine of the angle between the magnetic field lines and the normal line of the surface and the magnetic field lines. The next 4 slides are questions followed by answers regarding magnetic flux. At times, pause the video and practice these 2 problems. Now let's move on to Faraday's law of induction. His law states that the induced EMF is equal to the number of loops in the wire times the change in magnetic flux. This can be either a change in area, a change in magnetic field, or a change in both magnetic field and area over a change in time. Well, what does Faraday's law of induction actually mean? This law states that a potential difference, EMF, is induced when the magnetic flux changes. This can either be a change in area, a change in magnetic field, or a change in both. Well, what does the negative sign mean in Faraday's law of induction? Well, the minus sign tells us the direction of the induced EMF in a current loop is such that the resulting current produces a magnetic field that resists the change in flux through the loop. This is called Lenz's law. This is a direct result of the law of conservation of energy. There are 3 simple rules of induced current with Lenz's law. The induced current, 1, points in the opposite direction to the external magnetic field if the external magnetic field is increasing. And 2, the induced current points in the original direction of the external magnetic field if it is decreasing. And 3, the induced current is 0 if the flux is not changing. It is 0 because of Faraday's law. There is no induced EMF and the magnetic flux is constant. At this time, you will practice 2 problems regarding Lenz's law. Answers can be seen on the following slides. Let's return back to the objective of this lab. The objective is to discover the different attributes that affect magnetic induction. Question 1. What happens when a magnet is moved through a wire coil? 1. Attach the coil of wire to the voltmeter using the metal clips. Set the ammeter measure in millivolts. And 2. Take the magnet and move it through the coil of wire. Record your observations below, then answer the question. Let's go over the materials necessary for this lab. You will need a battery, a switch, a rheostat, a voltmeter, and magnetic loops of wire, or coils, and a magnet. If you do not understand how to set up your circuit, please visit the video on series and parallel circuits. The following is a demonstration of the lab. Please watch the voltmeter as the experiment goes on. Well, what did we see? We saw that the movement of the magnet through the coils caused an induced EMF. However, there is no EMF when the magnet was sitting inside the coil. This can be explained by the magnetic field supplied by the magnet not changing with respect to the area encompassed by the magnet. Therefore, there was no flux through the system, hence no induced EMF. The induced EMF was negative at points due to the reversal of the direction of the magnet, i.e. being taken out of the coils. Question 2. What happens to the induced voltage if a magnet is moved through a coil of wire? 1. Attach the multimeter to the coil of wire and move a bar magnet through it. Then move the bar magnet through it. 2. Record your observation below, then answer the question. The materials necessary for this experiment are 1 ammeter, 3 sets of coils, and a magnet. Let's begin our experiment. Keep an eye on the ammeter as the experiment goes on. Now let's see what happens if we change the speed the magnet enters and leaves the coil. Well, what did we see? The movement of a magnet through the coils caused an induced current. This can be explained through the changing magnetic field over a stationary area. Therefore, there is a change in magnetic flux, which means an induced EMF. To oppose the increase in flux, an induced current is created to create a countermagnetic field to decrease the increase in magnetic field supplied by the magnet. In addition, the larger the coil, the larger the magnitude of the induced current. This can be inferred by Faraday's law of induction. The increase in coils increases the induced EMF, which increases the magnitude of the induced current. Thank you for your participation in this online lab. I'll see you next time.